So here we go, reviewing the last problem we did in class today, and it's really important. There's one point I want to make in this problem. So let's review the problem. The previous problem, just to make sure we understand, it's really, really important, is that the first problem we just had, okay, this weak acid, and I know it's a weak acid because of the very small Ka. That means the equilibrium position favors the undissociated acid, and here's the conjugate base. It's in this position. So that means it barely has any real pathway to go forward. The reverse is more spontaneous, which means the strength of the Kb, or this conjugate base, to absorb the H and reform the acid is more spontaneous. So when we have this sitting in water, it's going to reach equilibrium with its conjugate base, and it's going to favor the undissociated acid. And that's the equilibrium. We want to know what the value of X was. How much did this dissociate? And that's what we did here. The second problem here was that we did something called a titration. And what makes this a titration part of a problem is that this is straight stoichiometry, meaning I'm going to drive this reaction somehow. This reaction was driven forward. HA is terrible at dissociating, but this strong base is driving it forward stoichiometrically. If I have enough hydroxides, I could make every single one of these guys dissociate into its conjugate base and give up the H+. Now, of course, the H+ is going to travel to the OH- and become water. So that's absolutely important that you see that. And how do I know that? I see one single arrow and I see a strong base. When it's sitting in water, it's going to do its equilibrium thing, but when it's with a other compound, it's going to be driven. So what we did is we took some amount of the base, strong base, and there's my hydroxide, and then my weak acid, and we put them together. Now, party people, all we had to think about here was now we're driving the reaction. So what I did here is an ice table, but this ice table is based on moles because it's stoichiometry. It's straight stoichiometry. There's no equilibrium. So I'm after moles. And if you remember, molarity is equal to moles over liters. So if I give you the volume and I give you the molarity, you know the volume times the molarity, the liters cancel and left with mole. Only catch is I gotta make sure the milliliters are in liter. So I times my liter times my molarity, and I get my moles of both of these. And then I put them in a table like we've done before to find the limiting reagent. Because there's a coefficient of 1 here and a coefficient of 1 here, what do I know is, well, gosh darn it, in order to make all of the hydroxide disappear, I need to have at least 0.006 over here. It's a 1-to-1. Oh, I have more than enough. So all of the hydroxide disappears, and this is my limiting reagent. So this is my limiting reagent. Notice I start with 0.006 as I calculate the moles from the volume times the molarity, and then I subtract it. Notice I got 0 left. Limiting reagent, the reaction keeps going till you run out. And because I'm using 0.006 and this is a 1-to-1, this is also minus 0.006. Notice I have 0.01. So only 0.06 is going to be used. And remember, this is initial, this is the change, and this is at the end of the completion reaction. This is a driven reaction. So we minus that and we have some excess of hydrofluoric acid. And of course, if we're minus 0.06, because this is a 1 and this is a 1, it's plus 0.006 in both places. Okay, and because you add them to 0 at the end of the completion reaction, the driven reaction, we're left with some conjugate base and some HF left over. In the next question in D, they asked you for the molar concentration. They were asking for the molarity. So we take the moles of the F minus, that's remained, and notice whatever hydroxide was used up is exactly how much fluoride ions was produced, okay, because it's minus X plus X. Any case, I divide that by the total volume, and of course we're adding liquids together, so the total volume is 25 plus 15, which is 40 milliliters. I convert to liters because molarity has liter as a unit. Okay, I take the moles divided by the liters, and there's my value for the concentration of the fluoride ion. If I add this amount of moles of hydroxide with this amount of hydrofluoric acid to start with. Okay, so if you look very carefully, we drove the reaction and then it stopped when we ran out of hydroxide ions. Now, if you notice something, we did not reach equivalence point. If you remember what equivalence point is in a titration, an equivalence point is where we get to this point where the hydroxides equal the OH minuses. That's the volume of base that we add at this point would be the volume needed, okay, times its molarity, which equals the moles of OH needed for the OH to equal H plus. Okay, very important. Well, guess what? We're somewhere below this line, somewhere in this line here, because we have some acid left over and we have some what? Base left over. So we have over here we have some acid that did not react because there was initially more than the 0.06, and we have some what? We have some conjugate base that was made. Now look who's winning here. There's actually more conjugate base than conjugate acid. But in any case, all right, moving forward, this question just wanted this answer here, and I gave it to you. Now, the next question states, calculate the pH of the solution. This is important. The pH of the solution, okay, we need some more work here because now, just like we started in the first problem, we're going to have HF in water, and we're also going to have some fluoride ions in water. How is this going to give us a pH? Well, let's set up this equilibrium. We're not driving the reaction now, party people. It's another equilibrium problem. So let's write it. Again, we're going to have HF in water. Why water? Because that's the predominant species. It's now equilibrium. We've run out of the base. There's no more base. It was the limiting reagent, so it's gone. So now there's just water. And it's going to make H3O plus and F negative. Now, of course, the reverse reaction is that H could actually be accepted by the F and go in the reverse, but this is going to reach an equilibrium position. Let's write an ice table to understand what's going on here. This is an equilibrium ice table that uses molarities, initial concentration at equilibrium. So initially, what's the concentration? Now, when we do a equilibrium ice table, these things right here are going to be molarities. Okay, now the question is, we have initially 0.10. Now, you needed to calculate that. I did that already for you. I needed the concentration of HF. After this completion reaction finished, I had 0.004 moles of HF left over. I'm dividing that by 0.04 liters, and that gives me 0.10. So initially, I have 0.10 molarity concentration of HF. Okay, this is a liquid, so I'm not really going to change that. And then we had how much F? 0.15. So initial conditions, we have these things. That's important. We've seen this before when we had a common ion. Remember, in KSP, we had a beaker, let's say, of something that was saturated, and there was already concentration of ions in there, where we're saying the same kind of deal. All right. Now, what we're going to do is put a 0 here. We're going to say that there has been no H3O pluses have been produced by this acid. Remember, when we do equilibrium problems, I like to start from the position that this acid has yet to dissociate. And if I think about it, if there's 0 H3O pluses because this hasn't dissociated yet, then it must be a position where I'm starting with the Q really big or less than K, okay? Or Ka if you want to call it. So it's going to go forward. All right, so this is going to be the change. I'm going to lose something. It's going to go forward somewhat because I don't have enough H3O pluses. And I'm going to gain something. It's a plus X. Why is it plus X? Well, this is a 1 to 1 to 1 ratio. Okay? And of course, this is going to be plus X as well. So at equilibrium, party people, what do I have? I have 0.10 minus something. X plus 0 at equilibrium is X. And then here I have what? Okay, 0.15, let's do plus X, if you want to do it like that. And I know what the KSP of this is, all right? So really what I'm after is I'm after X. And once I have X, I can do the negative log of that concentration. So what do we know? The KSP of the forward reaction, I'm sorry, I say KSP, we've been doing it so much, the Ka. The Ka of HF is written for us as 7.2 times 10 to the negative 4. So 7.2 times 10 to the negative 4. That's my Ka. And of course, it's products over reactants. My products are this, so it's kind of X. Wait a minute. Before we put these values in, we know we're going to come up with a quadratic catastrophe. So this X and these X's, they're all small compared to these big numbers. Now we want this X. It's going to be a small value, so I'm not going to approximate that away. But compared to 0.1, because this Ka is so small, a Berry goes forward, we can approximate away these X's. And what I'm left with is products. I have X, that's from the H3O plus, times 0.15. I got rid of the X because this number is so much bigger than the X, we're approximating away, over the reactant 0.10. Okay, so when I do the math and solve for X, which means I'm going to times that by 0.1, okay, and divide by 0.15, I'm just going to do the algebra here. I get my X, my handy dandy calculator, to equal 4.8 times 10 to the negative 4. What did I solve for? A concentration. Concentration of what? I solved for the concentration, okay, of X, which is equal to the H3O plus concentration. I asked for the what? pH. So how do I take a regular concentration and make it into a pH? Well, party people, I do the negative log of the H plus or H3O plus concentration. So the negative log of 4.18, okay, times 10 negative 4, all right, of that value I just talked about is equal to 3.3. So that's our pH. Nice little equilibrium problem. No big deal. Okay, what made this a little different, party people, is that we started with some conjugate acid and some conjugate base. All right, now the reason for me making this extra video when I already have one made for this, I want to talk of another way to solve for this. Okay, so stay with me. We're going to do a little derivation fun. I'm going to get rid of this. Okay, you should know the answer pretty much. Get rid of all of this. I don't think this key is as clear as it could be, but hey, I'm tall. Now, this is something we have already done, so hopefully it inspires you to remember, or at least wakes you up a little bit. So here we go. What do we know? Ka is equal to, in this case, well, let's think of an acid, just general. Ha, is going to, in equilibrium, with H plus and A negative. The A negative, of course, is going to be the conjugate base. So here's the conjugate acid and the conjugate base. Now, if I write the equilibrium expression, it's going to easily be the products over reactants. Coefficients become exponents, and because they're all 1, they're all to the first power. Now, if I added water to this and made this H3O plus, it'd be the same. Water wouldn't fit in here. But here we go. Now, what I'm going to do is I'm going to do the negative log of both sides. Okay, so negative log of this, and I'm going to do the negative log of that. Now, negative log of this becomes something called the pKa. That should sound familiar. Now, I do the negative log of this expression. I'm going to break this up. I'm going to do the negative log of the H plus separately. Now, I can do that and then do the negative log of what's remaining in this fraction, and that would be the conjugate base concentration over the conjugate acid concentration. Now we know something. Negative log of the H plus is the reason why I separated it, is going to equal what? The pH. Ooh la la, look at here. The pKa is equal to pH minus the log of the conjugate base over the conjugate acid. I'm going to clean this up and solve for pH. All right, so when I solve for pH, I'm going to put plus log over here. So this becomes pKa plus the log of A over HA. Now this is called the Henderson-Hasselbalch, and I'll clean it up. So what we have is the pH is equal to pKa plus the log of the ratio of A over HA. Ha! Why is this really important? Well, this Henderson-Hasselbalch equation helps us solve for the pH if we have a ratio of what? The conjugate acid to conjugate base. If we have a ratio to conjugate acid, conjugate base, my friends in chemistry, we have buffer. We have a buffer. What's a buffer? Well, we have an acid and we have a base with some quantity that can actually keep a solution from its pH rising or decreasing because we both have an acid and base there. And as we learned, the conjugate acid base pair cannot interact with themselves because they are fighting for that equilibrium position. A conjugate acid base pair do not neutralize each other. So that's the only way to have acid and base remaining. Other acid and bases will react with them. So the same conjugate acid base pair cannot interact with each other because essentially, as we just saw yesterday, Ka times Kb equals Kw. All right, as strong as this is, as weak as this is. Okay, so going back to the problem and loaded with this formula, we can solve this problem without doing an ice table. Look what I have here, party people. Okay, I have HF as 0.10, so let's put 0.10 down here. That's the concentration initially of my buffer. I made a buffer. This titration was done to create a scenario. Was this titration done to completely drive off the HF? No. They added just enough hydroxide to create a buffer scenario so that we would make some F negative and still have some HF available. So this was done to create a buffer. So to solve for this, okay, look what I have here. 0.10 right here, and then 0.15. In 0.15, okay, in 0.15 divided by 0.10, I'm going to do the log of that. Okay, now 0.15 is the conjugate base. So let's go find that number. All right, very simple. So I'm going to do 0.15 divided by 0.1. And what I get is 1.5. Now I'll do the log of 1.5. Okay, log of 1.5 is 0.176. So what does that mean, party people? This whole expression right here is, in this case, is 0.176. What's the pKa? Well, to get to the pKa, what I'm going to do is I'm going to find the negative log of my Ka. So I have some extra work. So what's the Ka? The Ka was given to me to be where? Oh, 7.2 times 10 to the negative 4. So what's the negative log of that? So I do 7.2 second function EE. I like that better than a carrot, but hey, if you don't like your vegetables, I like my vegetables. But in any case, I'm going to take the negative log of that number. And what I get, the negative log of that number, is 3 points. So the negative log, remember it's a little p, of this number is equal to 3.14. That's my pKa. It's a Ka with a negative log is pKa. So it's so simple. So I put my 3.14, and then when I add these together, remember, pH equals the pKa plus the log of the ratio of the base and the acid conjugate pairs that are there. And what you have is 3.14 plus 0.176, and you get 3.3. So you could have done the problem this way. So the pH is equal to 3.3. Now, you may say, well, it's the same amount of work. Sure, but there's some really important implications here that you need to understand. Look at the value for 3.3. Why is that important? It's important because it tells me that's the pH of the buffer. That's the pH when you have that. Now, to review a little bit, we should know something about Henderson-Hasselbalch, okay? And we should know that if we have this scenario, remember, pH equals the pKa plus the log of the conjugate base over the conjugate acid. Now, what does this look like when I graph it? When I graph a titration curve, we know that this point, the asymptotic, is the equivalence point. That's where the H pluses equal the hydroxides. Now, if this is the halfway equivalence point, this is when I added half the amount of moles, let's say hydroxide, to neutralize. Wait a minute. If I was to neutralize this halfway, So if I started, look here, if I was to start with 0.10, and let's pretend I'm a princess and this number was 0.05. If this was 0.05 and I took away only what, minus 0.005, okay, wouldn't I have half left? And wouldn't these two numbers be the same? Right, if this is going to be 0.005 moles, right, and this is 0.01, and we're both in the same what? Do the math, 0.005. Wouldn't this be 0.005, right? Yeah, and if it would, good job out there, these numbers would be the same. And if they're the same, what's the log of 1? The log of 1 is 0. And if that's the case, pH equals pKa when we've what? Titrated halfway. So we can actually find the Ka of the acid. Now we find the pKa, but to get the Ka, we do 10 to the negative x of it to get the Ka. Right? Remember that? So in this case, the answer was 3.3. What was the pKa? Well, 3 point what? 14. But why was the pH of our buffer 3.3? It was a little higher. Why was it 3.3? Well, the answer to that is in our values. Look at here. Didn't we have a little more conjugate base than conjugate acid? You betcha. And because we had a little more conjugate base, the pH of that buffer was a little bit higher. Okay, hopefully there's some ahas here. If I had more conjugate acid, the pH would have been less, right? This ratio of conjugate base to acid makes it either go this way or this way from that position. But when they're equal, that's the max buffering position. We get rid of this, and pH equals the pKa. So to know if a buffer, what is the best place for this buffer? Now, buffers mean that the pH doesn't change much because we have what? We have conjugate acid who can react with, as conjugate base, can react with acid and neutralize it. And we have conjugate base can act with the acid, and then we have conjugate acid who can react with a base to neutralize it, but it would be another base, let's say OH minus, and give it an H. Okay, so an H would go from the acid that way, and we could basically, because we have both the acid and the base there, the pH doesn't change much. We call this the max buffering region because here's the only position when the pKa equals the pH that these values in this position would be exactly the same. That's the point I want to make. So the Henderson-Hasselbalch is a tool that we can use to solve for the pH and the amount if we have what? Conjugate acid and conjugate base present. That's important. And the idea here is that we created a buffer. This titration didn't go all the way to the equivalence because they wanted to create a buffer. And that's something we have to start to recognize as well. All right, so a lot going on there. Continue with your rest of your homework.